In this section, we'll talk about our official one sample z confidence interval. We use a z confidence interval if we know our population standard deviation sigma. So our level c confidence interval from u is going to be x bar plus or minus z star times sigma over the square root of n. Or if you want, you could just say x bar minus z star sigma over square root of n, and x bar plus z star sigma over square root of n. So this interval is exact when our population distribution is normal, and it's approximately correct if our sample size is large, at least 30 for any population. So we either need to start with a normal shape or have a large sample size. You notice I had here the z star. We call a z star a critical point. What this means is if I was to draw a normal curve, and if we want a level c confidence interval, we have c area in the middle, and this would be negative z star, and this would be z star. So when we did it previously, we did a 95% confidence interval, and we did 0.95 in the middle, and negative 1.96 to 1.96. And so we had z equals 1.96. That's what we mean by our z star. That's what we mean by our critical value, is it's how many standard deviations you have to be from the mean to get that 95% in the middle. Now you'll notice here that we're adding and subtracting a part. The part that you add and subtract is called m, or our margin of error. It's how much we're likely to be off by, or it's our margin of error when we estimate our population mean u with x bar, our sample mean. So C is called our confidence level, so that would be like the 95% is your confidence level. You could also write, we had x bar plus or minus z star sigma over square root of n. Notice that sigma over square root of n is the same thing as our standard deviation for x bar. So depending on how you like to write it. There is a condition. You should only find this confidence interval if you start with a normal population or you have a sample size of at least 30. So for our calculator, this is just our calculator part to find z star. So again, to find z star, z is for our standard normal curve. We'll set mu equal to 0 and sigma equal to 1, so we can use that standard normal curve. And in our TI or Casio, we'll just be looking for an inverse normal function. Okay. I had here that for the TI you have to use the area to the left, but it does look like our updated version you can use areas to the left or in the middle. So you can go ahead and try to find z star for a 90, 95, or 99% confidence interval. Remember again, if you want 90%, then that means you'll draw a picture with 0.90 in the middle, and you'll be looking for z star that gives you 0.9 in the middle. So we have a problem for you to try. Make sure after you try a problem that you read through this warning. This is very important. Okay. Let's try one now for us. We have a sample of 100 bank customers with a mean waiting time of 5.46 minutes. So n equals 100. X bar equals 5.46. Notice it was for our sample, so that's our sample mean. Assume the standard deviation for all. Now when you see all, that means population. So our population standard deviation is 2.47. Oh, let's see, we were supposed to summarize it all with our appropriate symbols. That's what I just did. Let's check our conditions. It needs to be either normal or n of at least 30. Our sample size was 100, so we're good there. Let's find the critical value for a 99% confidence interval. So that means we have 0.99 in the middle, and I need to find this z star that will give that to me. So I'm just going to use my confidence interval, or calculator, and look for the inverse normal function. Okay, so I'll use second distribution. I'm looking for inverse normal. The area in the middle is 0.99. My mean is 0, standard deviation is 1. I want the area in the center. And notice it tells me that I'm going from negative 2.575 to positive 2.575. So we have z star equals 2.575. Now, if you needed to in your calculator have just the area to the left, you can say, well, what is 1 minus 0.99? That gives me 0.01. And if I try 0.01 divided by 2, that gives me 0.005. So I could say there's 0.005 in each tail. And I could look up 0.005 to the left, so I could do second distribution, inverse normal again. And I could do 0.005 area to the left. And notice it gives me negative 2.575, and then I could by symmetry say z star is just 2.575. Okay, now let's find our 99% confidence interval. So our formula is x bar plus or minus z star sigma over the square root of n. Oh, I better zoom out a little bit more. So x bar is 5.46 plus or minus our z star, which was 2.575. My standard deviation is 2.47, and n is 100, so square root of 100. So we have here 5.46 plus or minus 0.636. So if I do 5.46 minus 0.636, I get 4.824, and if I do the plus part, 5.46 plus 0.636, I get 6.096. So that is my confidence interval. So to interpret it, that means we're 95% confident mu is between 4.824 and 6.096. So 95% confident mu is between those two numbers. That's kind of our cut and dried version. Now let's actually interpret this. So remember, we're talking about waiting times at the bank, and we want to know what the mean waiting time was for all the customers. So we could say, if we're trying to make it nice and simple for our boss, we say something like, we are 95% confident that the average waiting time for all, notice I have two keywords here. I have the keyword average and all to tell me it's for the population. For all customers is between 4.824 and 6.096 minutes. Again, two words here you have to have, average and all. Oh, and I said 95, that's just habit. We actually found a 99% confidence interval, so let's make sure that's 99% confident. Which 99% confidence seems pretty good, right? That means for every sample I could have chosen, if I found confidence intervals for all of them, 99% of those confidence intervals would actually contain our population mean mu. Oh, and I guess I just needed to say that here. So what does the 99% confidence mean? It means of all the possible samples I could have chosen, 99% of the resulting confidence intervals would have actually contained the population mean mu. Now, this is a different kind of situation again, where I actually have the data for all of the bank waiting times. We usually don't have the data for the entire population, but I do in this situation. And the true population mean is 5.69. So that means mu actually is 5.69. Again, our population mean mu was fixed. It wasn't changing. My population mean is not changing. I just didn't actually know what it was, but it is 5.69. Now, our 99% confidence interval is 4.824 to 6.096. So, did our confidence interval contain mu? Yes. 5.69 is between 4.824 and 6.096. Now, I did a little graph here, so you can see this histogram is a histogram of all the individual waiting times. That means the actual population. And you can see this little line here, that's the actual population mean. So that line is at our 5.69. Okay. And then right here, notice this right here, this is our actual confidence interval. Notice how small our confidence interval is compared to our entire population. When you take bigger sample sizes, your confidence intervals get smaller and more precise. Okay. So it looks like our confidence interval is very small compared to our original population, which tells you that it's going to be more useful when we want to actually calculate our population mean or estimate our population mean. So our confidence interval is 4.824 to 6.096. Now Sean tried to interpret his confidence interval as 95% of the waiting times will be between 4.824 and 6.096. So here's our 4.8, 6.0. So this is a common thing I see people try and say. It's absolutely wrong. Let me show you why. Okay. Notice again, this blue histogram is our histogram of all our individual waiting times. This confidence interval is from 4.8 to 6.0. Does it look like most of our waiting times fall within that very small window? No. The actual values have a much wider spread than our actual confidence interval. So our confidence interval is always smaller than our actual individual values. So, no. Our individual values in the population will always be much more spread out than the confidence interval. Okay. Also, so that's just kind of to help you believe it, but also confidence intervals tell you something about the population mean. They don't tell you anything about the individual values in the population. So anytime you read something like this and they try and give you an interpretation like 95% of all the actual individuals will be within the confidence interval, that's going to be wrong. It doesn't tell you anything about the individual values, and if you were to actually graph it out, the individual values have a much wider spread than our actual confidence interval. Okay, and this just leads us into correct interpretations of confidence intervals, because again, the most important thing you can leave this class with is how to interpret it correctly. Calculators will calculate everything for you. You have to be able to interpret it. So correct interpretation is we would say something like, we are 95% confident that our population mean is in our interval. And the actual 95% confidence level means if we took many, many samples, 95% of the samples would give us a confidence interval that actually contains mu, our population mean. So we're fairly confident that our interval contains our population mean mu, but there's no way to know for sure. Now, notice this is the correct interpretation. This is what the 95% confidence level means. If you see any other interpretation, you know it's going to be wrong. Here are some very common ones that are absolutely wrong. Make sure you don't write these. So the confidence interval does not tell us anything about the individual observations. That's what we just did up above. The interpretation should not say anything about the sample mean, because it's supposed to talk about our population mean. And we don't say that there's a 95% probability that mu is in the interval. The reason for this one is the population mean mu is fixed. We don't know what it is, but it isn't changing. So it is not a random variable. Because it isn't random and it isn't changing, we don't talk about probability. Okay. Instead, it is which sample we chose that changes. And then that affects our sample mean and our actual confidence interval. But the population mean mu itself is fixed. It's not changing, so there's no probability attached to our mean mu.